Subchapter 4.3 The Simple Rankine Cycle. This modified cycle is called the Simple Rankine Cycle. The Simple Rankine Cycle has the same component layout as the Carnot cycle, but instead of compressor, Simple Rankine Cycle using pump. There are 4 processes involved in a Simple Rankine Cycle. Isentropic compression in pump for process 1 to 2. Note that pump utilizing power during the operation. Therefore, for process 1 to 2, we're going to have terms W.in. For process 2 to 3, we're going to have constant pressure heat addition in the boiler. For process 2 to 3, we're going to have terms Q.in. For process 3 to 4, we're going to have isentropic expansion in the turbine. For this process, we are going to have terms W.out, while process 4 to 1 is constant pressure heat rejection in the condenser. Therefore, the term Q.out is related to this process. A few assumptions will be made during the thermodynamic analysis for a simple Rankine cycle. They are steady flow process and ideal process. The pump and turbine are adiabatic. Therefore, the term heat transfer will be neglected. Meanwhile, for boiler and condenser, since they are not a work-producing or consuming devices, therefore, the terms work in and work out will be neglected. Since we are assuming all the steady flow devices works ideally, therefore the terms potential and kinetic energy for all components will be neglected. And lastly, we are going to assume that this cycle obeys conservation of mass principle. Now let's have a look at each devices. For process 1 to 2 at the pump from the steady flow energy equation, since the pump consume power during the operation and we neglect the terms heat transfer rate, kinetic energy, power out and potential energy, we are going to have this expression. Based on the derivation of isentropic process for 3 different substances as discussed in chapter 3, we have this expression. Since the pump works isentropically, therefore the terms ds will be equal to 0, which leave us with this expression. If we integrate this expression, we can get this equation. If we substitute the change of the enthalpy to the steady flow energy equation for the pump, we are going to get this expression. If we divide the mass flow rate to these equations, we are going to get these equations. Note that these equations will give us in the unit of kilowatt or kilojoule per second, while these equations will give us in the unit of kilojoule per kilogram. The next device is boiler. Note that state 2 is the inlet of the boiler and state 3 is the outlet of the boiler. From the steady flow energy equation, since the boiler receiving heat, therefore the terms Q.in will be remain in the steady flow energy equation. Based on our assumptions, we can neglect the terms Q.out, power, kinetic energy, and also potential energy. Our steady flow energy equation will now become this expression. If we divide the mass flow rate to this equation, we are going to have this expression. Note that Q.in equal to m dot H3 minus H2 will give us in the unit of kilowatt or kilojoule per second. Meanwhile, Qin equal to H3 minus H2 will give us in the unit of kilojoule per kilogram. For process 3 to 4 at the turbine, from the steady flow energy equation, we can neglect the terms heat transfer rate, kinetic energy, and potential energy based on our assumptions. Since turbine producing work, therefore the terms power in can be cancelled. Our steady flow energy equation for process 3 to 4 will become this equation. Note that state 3 is the inlet of the turbine and state 4 is the outlet for the turbine. Our steady flow energy equation will now become this expression. Again, if we divide the mass flow rate to this equation, we are going to have this expression. Note that different expressions will give us in different unit. Lastly, for process 4:1 at the condenser, from the steady flow energy equation, we can neglect the terms power, kinetic energy, and also potential energy, since the condenser only rejects heat from our system. Therefore, the terms Q dot in can be cancelled. Our steady flow energy equation will now become this expression. Note that state 4 is the inlet for the condenser and state 1 is the outlet of the condenser. Therefore, the steady flow energy equation for process 4:1 at the condenser will now become Q dot out equal to m dot times H4 minus H1. This equation will give us in the unit of kilojoule per second or kilowatt. If we divide this equation with the mass flow rate, the equation will now become Q out equal to H4 minus H1, which give us in the unit of kilojoule over kilogram. The thermal efficiency for Rankine cycle is given by power net out divided with heat transfer rate in, or equal to net work out divided with heat transfer in. Note that the value for the thermal efficiency will be in between 0 to 1. Power net out is given by power out minus power in, and net work out is given by work out minus work in. From the Rankine cycle, we can determine the work ratio that is given by the ratio between the net work output divided with the gross work output. We can also determine the specific steam consumption, or in short, SSC. Specific steam consumption is given by m dot divided with power net out, or 1 divided with net work output, where the unit will be in kilogram per kilojoule. If we use the equation of 3600 divided with the net work output for the specific steam consumption, we are going to get in the unit of kilogram over kilowatt hour.